All right, so I wanted to say a little bit more about fractals, which is just, this is not exactly, part of the course per se, but I thought it was interesting about the Cantor set I said at the very end is a fractal. The Cantor set is an example of a fractal, and the important property of a fractal is that when you scale it up, you see basically the same thing again at a different scale. So the simplest example, and this is sort of so simple as to be not interesting, is just an interval, say 0 to 1. If I scale this up, let's just, for this, to make it interesting, let's scale it up times 3. What does it look like? It looks like, it still looks like an interval, although it's like 3 times bigger now, all right? What I see here is 3 copies of the original thing, all right? And this is the basic property of a fractal, that when you scale it up, you see, again, copies of the same shape. The Cantor set is like this too. So if I were to draw, I'll try to draw the Cantor set. It is, you take the interval, but you remove the middle of the interval, and then you remove the middle of the middles, and you remove the middle of the middle of the middles. It looks, something like vaguely like this. This is what you get after. Take the whole interval and you remove the middle third, and then you remove the middle thirds of those which remain, and you keep on removing the middle thirds forever. You get sort of like a dust of points, which is not equally distributed here. It sort of only lives in these little clumps, all right? What if I scale this one up times 3? Now, this all lives from 0 to 1, right? What if I scale this one up, x3 it? Well, I guess instead of stretching from 0 to 1, the whole thing is now going to stretch from 0 to 3, right? So it now goes from 0, 1, 2, 3, right? This is 0, this is 3 now. The part in the middle is going to be gone, because that this gap in the middle here is going to stretch out to be this gap in the middle here. And each of these little guys goes over here, and if you think about it, actually, everything looks exactly the same. The middle of this one is removed, the middle of this one is removed. You get the same thing again. Only now what we see is actually 2 of them, right? Here I have 2 copies of the original. I scaled it up by a factor of 3, and what you end up with is 2 Cantor sets with like a big gap in between them, all right? This is what being a fractal is all about. Any thoughts about that? There's an interesting interpretation of this in terms of dimensions, and I think this is a great thing to talk about on the playground with your friends. Once you're done talking about different sizes of infinity, there's an interesting thing about dimensions of fractals. So I will remind you, the first thing I said was, if you just take an interval and you scale it up times 3, what you end up with is 3 intervals, right? 3 copies. What if I do the same but like one dimension up? If I start with a little square, a unit square or something, and I scale this up, again, let's do 3 times. I don't get 3 copies of the square if I scale this up like in R2. If I scale it up, actually what you get is this, right? If you take a unit square and scale it up by a factor of 3 in R2, you actually get 9 copies of the unit square. This is 9, which I will suggestively write as 3 squared copies. Why do you get 3 squared in R2, whereas you only get 3 in R1? Basically, it's because R2 is 2-dimensional, all right? And this is part of what we mean when we say R2 is 2-dimensional, because things grow differently in R2 or something like that. This is another point of view about what dimension is supposed to mean. And what about in 3 dimensions? So if I start with a little cube and I try to inflate it by a factor of 3 in all directions, well, there are now 3 directions to go in, and what you get this time is something like I guess like a Rubik's Cube, right? With 3, something like that kind of thing. And how many copies of the original cube are in there? It's 27, yeah, if you think about it a little bit, or you could try and count them up. Smash a Rubik's Cube and count up the pieces. There's 27. You got to include the one in the middle, which isn't a real piece in a Rubik's Cube. But anyway, this is 27, which is 3 cubed copies, all right? This number, this exponent, is the dimension of the object that you're talking about. The first one here was 3 to the 1, all right? That exponent there is the dimension. This is another way of defining the word dimension. Probably you've seen a definition of the word dimension in linear algebra, the definition or the dimension of a vector space. You all remember the dimension of a vector space? It's the number of elements of a basis for that space. You have to know that for the comp. Maybe you forgot that since your linear algebra class. But anyway, this is another way of defining the concept of dimension. These things are not vector spaces, so you can't use the linear algebra definition, but this is another way to define the dimension. And in this context, this type of dimension, you know, it's a different, it ends up giving you the same answers, but it's a different definition than we use in linear algebra. This is called, this exponent is called the fractal dimension of the object. Fractal dimension. Or this also has a person's name. Sometimes this is written as Hausdorff dimension. Hausdorff is one of the sort of OGs of topology. But it's also called the fractal dimension. This definition only makes sense if you're talking about fractals, because it's all about if you inflate the thing, how many copies of the original thing do you get? Now, in an ordinary shape, when you inflate it, you don't get copies of the original thing, but in a fractal you do. So this is called the fractal dimension. All right, it's that exponent. When you inflate it by a certain scale, what is the exponent of what you end up with? What's interesting about this is, so the Cantor set is a fractal. What is the dimension, the fractal dimension of the Cantor set? So the Cantor set, you know, whatever, the picture, I don't want to draw the picture again. I go x3 on it, and what you get is 2 of them, right? 2 copies. So what's the dimension of that? Remember, the way you find the dimension is you look for an exponent of whatever the scale factor is. It's the exponent here. An idea? 2? It's not 2. If it were 2-dimensional, then this would say 3 to the power 2, because that 2 is the dimension. Any ideas? What is the dimension? What we have to do is you have to look at this number and write this as 3 to what power? That will be the dimension, whatever that exponent is. Yeah, this is a weird number. It's the log base 2 of 3. So this is, you can't write it the good part. The fractal dimension of the Cantor set is log base 2 of 3. This, of course, is an irrational number, right? This is like point, you can do this on your calculator, 0.631, etc. That's the dimension of the Cantor set. It's less than 1. So it is a fact that the fractal dimension of a fractal can be a non-integer. That's the interesting thing about the fractal dimension. It doesn't have to be a whole number. I don't know if you ever talk about this on the playground. Is there such a thing as like dimension 1/2 or dimension 2.5? The answer is yes, that is possible for a fractal. And the Cantor set has this dimension, 0.6. So my interpretation of what is it even, like, how should you think of something which is dimension 0.6? How I think of that is it's like almost a line. It's a little bit less than one-dimensional, right? Which is, I mean, that is kind of what the Cantor set is like. The Cantor set is, I mean, you might say a reasonable thing to assign as the dimension of the Cantor set, maybe 2/3, about 2/3, because you removed a third of it, right? So it's kind of like a line, but I cut out a bunch of stuff. It's actually not exactly 2/3. It's a little bit less than 2/3 because you don't only remove the middle, you remove even more stuff, all right? This is the fractal dimension of the Cantor set. Yeah?
If you don't scale it in thirds, like, what? Is it not? Like,
Yeah, if you don't, in all of these cases, this dimension here is invariant to exactly how much you scaled it. So for the line, well, for the square, for instance, if I square by a factor of 3, I end up with 9 little squares. If I square by a factor of 4, if I scale by a factor of 4, I would end up with 16 little squares. So you're going to get the same value for the dimension regardless of what scaling you use. Now the Cantor set is inconvenient to scale by things other than multiples of 3, because if you scale it by some other amount, you won't clearly be able to count how many copies of the original that you end up with. So it's only it's most convenient to talk about scaling by a factor of 3 for the Cantor set. Yeah.
Just one more. If you do have those different versions of the Cantor sets, like the fourths or whatever,
Yeah.
then you would like scale it by that
Yes.
number.
Yeah, and they would have slightly different fractal dimensions. So instead of removing the middle third, if you remove the middle fourth, say, that would be a little bit bigger dimension. Still not 1, but since you removed a little bit less. Yeah. So I thought it might be fun. Let me just say, fractals. This is the big punchline here. Fractals can have non-integer dimension. Non-integer, I mean not a whole number. Although it can't be negative. It's the fractal dimension is never a negative number, but it can be not a whole number. And I thought, just for fun, there's a great Wikipedia page that I thought we might scroll through together. It's called List of Fractals. I don't know if you've ever looked at this. By Hausdorff dimension. That's the same as fractal dimension. It has a bunch of pictures of different fractals that people have studied and what their dimensions are. So I thought just to like give us a feel for what these non-whole number dimensions even mean. So this is the page, List of Fractals by Hausdorff dimension. And you can see, here's this, the second one in the list is the Cantor set, and there's the dimension log base 3 of 2, which is 0.63, whatever. That's the Cantor set. This one here, the next one down, they call it 1D generalized symmetric Cantor set. That's when you remove something other than the middle third. So this picture here is removing the middle fifth. That gamma equals 0.2 means the gamma is the size of the part in the middle that you cut out. And actually there's a formula. This here is the formula for what's the dimension of the resulting thing based on gamma. So you could plug in gamma equals a third, you get this, but in more generality, it's that formula. I think that's kind of cute. The next one down, 1/4, 1/2 asymmetric Cantor set. That's when it says built by removing the second quarter. You remove the second fourth, not the one in the middle, but offset a little bit. You get a different, slightly weird dimension in that case. These are weird examples. Anyway, I'm going to skip over some of them. Here's another something like a Cantor set. This one here is interesting. This puffy thing is called a Julia set of a particular function. That is a super wiggly line, and if you zoom in to this, it looks like a nice sort of puffy thing. If you zoom in further and further, you will see the same wiggly pattern repeated however much you zoom in. This one, the fractal dimension is 1.08. That is a little bit more than a line. So if it were just like a circle or an oval shape, that would be just a line. It would be dimension 1. But this has some sort of super jiggity-jaggities in it, which makes it a little bit more than dimension 1. Very strange. There's some more. These are in increasing order according to their dimension. So these ones which are a little bit more than 1 basically look like lines, but they have lots of jiggity-jaggities in them, which give them a little bit more dimension. This is the dragon curve, which has, I guess, this is the 2-dimensional, they call it the Cantor dust. You can do the same thing as a Cantor set, but you start with a square and then you remove sort of, it's like you remove the middle third of each of its 2 sides and then block that out from the inside of the square. That has dimension like this. Here's these are some cute pictures if you are into that kind of thing. These ones, you can see these are still super wiggly curves, but they are the sort of wiggles are more densely packed in, and that makes the dimension even a little bit higher. That's a pretty good one. I don't know if this is, okay, they rounded it. I don't like how they rounded that. Come on. I thought, isn't that remarkable? You get actually 1.667? No, it's not. It's 5/3. Less interesting than it looks. Okay, let's see some that are more than 2. So more than 2 dimensions, I would imagine it's something like a plane, but super jaggedy, so that it's like a little bit more than 2 dimensions. And that's what these are all exactly 2. Sometimes you do get a whole number. But okay, like something like this is like a plane, but it's got sort of infinitely fine little bumps all over it, or something like that. Fractal pyramid. Yeah. These are great. I don't know if you think these are great. Some have dimension exactly 3. And then here's something very interesting. Random and natural fractals. People have tried to apply the same kind of analysis to objects that exist in the real world. There are some real world objects which are kind of super jiggity-jaggedy when you zoom into them. For instance, the coastline of Ireland apparently has been measured to have a fractal dimension of around 1.2. This was done in some research papers that you can read about if you like. It says, I like this little note here, there are marked differences between Ireland's ragged west coast, about 1.26, and the much smoother east coast, about 1.1. Well, yeah. Coastline of Great Britain, this has been studied a lot. This actually, the coastline of Britain was one of the first real-world objects that was analyzed in this way according to fractal dimensions by Mandelbrot, who is one of the big names in this. Here is coastline of Norway. All right. Balls of crumpled paper. I like that one. I don't. 2.5. I don't know how exact this analysis is, but here is sort of famously the surface of broccoli. 2.7. The surface of broccoli, they are considering only like the surface of it. It's super wiggly, and there's apparently they measured cauliflower to be. This is the same person who measured broccoli and cauliflower. Cauliflower is a little bit more than broccoli, I guess. The surface of lungs. Yeah, interesting stuff, I think. I don't know if you're into that. Any thoughts or questions about that? Yeah.
Can't wrap my head around. What do you mean like more than 2 dimensions? What is the? It's not like the dimensions really say this is 2D. It's not the same.
Well, it's the fractal dimension. I mean, like this says the surface of lungs 2.97. That's almost 3. But they're talking about just the surface of just like the edge of your lungs. The fact that it's almost 3, I guess this is because I don't know anything about the lungs. Are they like super wiggly or something? Like when I breathe in, there's just sort of one space that all the air goes into. There's not like separate chambers, right? but that one space is surrounded by an extremely floppy and wobbly edge, I guess. I don't know. This is strange but true stuff. I actually don't know much about the techniques that are used to make these kinds of specific measurements. I don't even know that word. The alveoli of a lung. Yeah.
Does the fractal dimension mean that no matter how much you zoom in, it's the same thing?
Yeah, that's something that actually I don't fully understand about. Like, these surfaces are not mathematical fractals in the same way that that we have been describing. Like when you zoom into a cauliflower, you don't like see more cauliflowers. I think maybe at some level that's true, but I mean eventually you get down to the last flower or something, right? But I think maybe they are sort of saying, well, if I zoom in, say like right here, that part of it does look the same as the whole of it, and maybe that's still true. Maybe you could zoom in one more level and that would still be true. Maybe they're assuming that if that same pattern persists forever, then I can measure the dimension. Yeah.
Is there a way to get higher with your dimensions? Or like, is that just not possible?
Yeah, you wouldn't be able to like look at it, or so like there's no physical object that is higher than 3 dimensions. Yeah, the best you could do would be more than 2, but less than 3. Yeah.
And you can't actually make a purely fractal object really the one that keeps zooming in the same thing.
Like mathematically, you mean?
Yeah. Is that fully the theoretical concept?
Yeah, like I'm not sure what you mean, but like these kinds of things.
Yeah, can you print those and like make those? Is that really?
I don't know if that's a photograph. I mean, you could try to 3D print something like that, although it wouldn't be infinitely detailed. You know, at some level, your printer will straighten out the edges. Yeah, yeah. These are all interesting things. This will not be on the test, but I just thought it was interesting stuff to chat about briefly. All right, great. Let's talk about something a little bit more down to earth then. All right. That was all about the Cantor set. It is a weird closed set. The next, I want to move on to another section, which is still on the general topic of topology of sets. The next type of thing we're going to talk about is called compact sets. You know, we talk about open sets and closed sets. Compact sets are not something that you've likely ever talked about in, say, calculus. I mean, everybody kind of knows about open intervals and closed intervals as being like the standard types of open sets and closed sets. Although compact sets are kind of about something a little bit different. They're like closed intervals. So let me just say a closed interval. Closed intervals are nice. Actually, closed intervals are compact sets and open intervals are not. But closed intervals are nice. And many theorems in calculus are about closed intervals. I don't know if you even remember the theorems from calculus. My experience teaching calculus is they don't care about the theorems. They just want to take the derivative over and over or something like that. Many theorems in calculus, though, are about closed intervals. For example, I will remind you, most people remember the big theorems from calculus. For example, there's a theorem that says if I have a function from a closed interval to R, usually I don't write it this way in a calculus class. If a function like this is continuous and f of a is less than 0, which is less than f of b, then there exists c in the closed interval with f of c equals 0. Anyone remember this theorem from calculus? This has a name. It says if you have a function on a closed interval and the left endpoint goes to a negative number and the right-hand point goes to a positive number, then in between, no. The squeeze theorem it involves an inequality like that, but it's not this. If you have one value that's negative and another value that's positive, then somewhere in between there's a value that equals 0. That's what there's a name for this. Remember this? This is called the intermediate value theorem. There's if there's a negative value and a positive number, then somewhere in between there's a value which has to be 0. All right. So this is an example of a calculus theorem that is about closed intervals, right? This is about a continuous function with the domain being a closed interval. Or even something like the nested interval property. That's a theorem about closed intervals, nested closed intervals. But the question is, I want to say, is this really about closed intervals, like specifically? Or maybe these things are true of any closed set? I don't know, maybe just like when you were in a calculus class, they just talked about closed intervals because that's just like something everybody knows about. But maybe these things are actually true in more generality. Maybe these are true for any closed set. Or maybe they're true for some other more general category. So is it really true about closed intervals? People talk a lot about closed intervals, but maybe the closed interval is not really what it's about. It's really about some more deeper property. I'm going to say closed intervals actually have a lot of nice properties. Closed intervals are most of the properties that it comes down to that are useful in calculus. First of all, closed intervals are closed, like they're closed sets, right? So you should think maybe those calculus theorems, maybe they're just theorems about closed sets. Maybe they're not closed intervals per se. Also, closed intervals there are two other important topological concepts that we haven't talked about yet. One is connected, which we will talk in more detail about this. Although I hope you have some idea of what I mean by connected. I mean just like it's all sort of one piece, not like the Cantor set, which is super disconnected. The Cantor set is like totally exploded so that it has infinitely many tiny little bits, but a closed interval is connected. Maybe that intermediate value property, actually it is a fact, that intermediate value theorem is actually true of any connected set. It doesn't have to be a closed interval. It's just a set which is all connected together so that if you're negative somewhere and positive somewhere else, you can sort of smoothly go through and you get 0 somewhere in the middle. And the third sort of thing that a closed interval is it is compact. And this is what I want to talk about today. And next time, sorry, something's not right with my pencil here. The closed interval is also compact. It turns out, actually, the nested interval property is not really a property of closed intervals. It is true of any compact set. Part of the important properties that are associated with closed intervals are just because they are compact. So let's talk about what does it mean to be compact. After compactness, we're going to talk about connected sets, and that'll be the end of our little topology chapter. Anyway, I'll tell you the definition. Of these three, compactness is probably the most complicated to understand. Connected is a very simple concept. Closed sets we already talked about. Anyway, compact set, what it means, I'm going to say a set K. Our book likes to use K for compact set. Of course, a subset of the real numbers is called compact when it's about sequences. If, say, AN is a sequence of points of K. So you imagine any sequence of points taken from your set, then basically I want to say it converges to something in K, although you can't actually say that. It's basically never true that any sequence in your set converges, because you can always do something like 1 minus 1, 1 minus 1, 1 minus 1. No matter what the set is, you can just alternate two values and that won't converge. So the best you can say is if any sequence of points in K, then it has a convergent subsequence. And the limit of that subsequence is in K. This is what it means to be compact. Any sequence in the set has a convergent subsequence, and what it converges to is also in the set K. All right, that is a compact set. As the standard example of a compact set is a closed interval. A closed interval is a compact set. Let's just do this as a standard example. A closed interval, I'll write it like, how about C to D is compact. Let's see if we can demonstrate that. This is not hard to do. What we have to do is consider any sequence of points in the closed interval, and then we have to explain why does it have a convergent subsequence, and furthermore, why does it converge to something which is still in the closed interval. So I'm going to say let an be in CD. I use the element sign there. I mean that this is a sequence, and each term of the sequence is an element of the closed interval. All right? We have to explain why does it have a convergent subsequence. Can anybody explain? How do you know? This would have been a nice, easy test question, maybe. How do you know that if you have a sequence, all the terms are in a closed interval, then it has to have a convergent subsequence? Yeah. Yeah, the Bolzano-Weierstrass says if a sequence is bounded, then it has a convergent subsequence. And if you have a sequence in a closed interval, then it's bounded, right? It's bounded above by D and below by C. So let this be in here. AN is bounded. So it has a convergent subsequence. By the Bolzano-Weierstrass theorem. BW. All right. Okay, that was the first part of the definition. Compactness says any sequence in your set has a convergent subsequence, and the thing it converges to is also in the set. So, anybody feel like you know? How do you know that what it converges to is still in the closed interval and not somewhere outside the closed interval? You have to, if you imagine this sequence in a closed interval, you know, I got C and D like this, and I have a bunch of points, right? Maybe they converge to something on the inside. Maybe they converge to one of the endpoints, C or D. Could they converge to something outside? I don't think so. Anybody? There's actually a simple way of saying it for the sake of trying to write down a formal argument. Yeah?
C is less than or equal to AN, which is the same as CD.
Yeah. This is different from what I was going to say. She said, yeah, AN, each term of AN is between C and D, and then because of the order properties of limits, it means the limit is also between C and D, which means it's not outside of the closed interval. Yeah, that's great. Maybe that's better than what I was going to say. I was just going to say, we already know the closed interval is a closed set, which means it contains all of its limit points. And so this, whatever this approaches, it approaches a limit point, and it has to be in here. It can't be outside of the set. So can I just write what I said? Because it's shorter. But what she said may be better, because it doesn't rely on old knowledge. But I will just say, since C to D is a closed set, the limit is contained in C to D, right? Because a closed set contains all of its limit points, and so if you do have a sequence in there that converges to some limit, the limit it needs to be in that set. All right. So a closed interval is compact. Actually, what what was important about this little argument is, first of all, we said that it was bounded, and secondly, we used the fact that it was a closed set. In fact, this would work no matter what the set is, as long as it's bounded and a closed set. All the same business will still be true, right? I didn't really use the structure of the interval. I just used the fact that the interval is bounded and then the fact that it's a closed set. So actually, this is a theorem. We don't need to belabor the point, but any bounded closed set is compact. The fact that it's bounded means that your sequence has a convergent subsequence, and the fact that it's closed means the limit of that sequence will be in the set. So any bounded closed set is automatically compact. That means that there are many examples of compact sets. For instance, the Cantor set is compact because it is bounded and it's a closed set. That's what we talked about last time. The Cantor set was a closed set. So something like the Cantor set is compact. Something like, a much simpler example, 1, 2, 3. This is compact because it is bounded, certainly, and it's also a closed set because it has no limit points. Right? Many things are compact sets. What about something that's not a compact set? Actually, this is not compact. The open interval, or any open interval really, but specifically the open interval 0 to 1 is not compact. What does it mean to be not compact? I guess it means that either it has a sequence with no convergent subsequence, or it has a sequence with a convergent subsequence, but the limit is not in the original set. So to demonstrate that it's not compact, can anybody think, this is not so hard to think of, a sequence of points which are all in this set, but their limit is not in here anymore? Yeah? Yeah, how about 1 over n? I was giving some hot advice to someone before the test the other day, and I don't think I ever realized this about myself, but when I'm trying to think of an example sequence, I always think of 1 over n. That's like my favorite sequence. My other favorite sequence is n. That also is very useful. N and 1 over n get you very far in life. Sometimes you want to do like 1 plus 1 over n. You want to get fancy about it. But those are the basic sequences. I suppose minus 1 to the n is another good one. Anyway, this is because, 1 over n. This is, each of those elements are in the interval 0 to 1. But the limit is not in 0, 1. Right? And this violates the definition of compact. Compact says every sequence in the set has a convergent subsequence. This one certainly does have a convergent subsequence, and the limit is also in the set. That is violated by this sequence here. All right? In fact, you can always kind of do this if the point of this is that that's not a closed set, right? If it's not a closed set, it means you can have a sequence of points which are approaching a limit, but the limit is not in there because it's not a closed set. So actually, any non-closed set is not compact. If you exclude the several nots in there, a non-closed set is not compact. This is maybe clearer if I write the contrapositive. This says if a set is not closed, then it is not compact. What's the contrapositive of that? Yeah. No, I don't think so. This says if it's not closed, then it's not compact. Yeah, if it is compact, then it is closed. So this, I'll write that as a theorem too. Any compact set is closed. Yeah. So if your set is not closed, then it cannot be compact. All right? Great. Here's another example of something which is not compact. How about all of R? Is this compact? It's not. This is not compact. I think actually this is where the word compact comes from. It's like too big. Remember, compact means every sequence has a convergent subsequence, and what it converges to is in the set. In this example, I can think of a sequence which has no convergent subsequence. Anybody know what I'm talking about? A sequence of real numbers which has no convergent subsequence. Just n. Yeah, is that what you were going to say? Yeah, just n has no convergent subsequence. It's unbounded, so it can't converge. R is not compact. For example, n as a sequence. This is a sequence with no convergent subsequence. Right? In fact, you can always do a trick like this. So R is not compact because I can choose n, and this sequence just gets bigger every time forever, and that means it doesn't converge. It's unbounded and increasing. In fact, you can do this not just for R, but any unbounded set. As long as the set goes on forever, as long as you can continually pick bigger and bigger values in your set, then that set will not be compact. So this is the same for any unbounded set. Unbounded set. An unbounded set is not compact. All right, and writing that in the contrapositive is a little clearer, just because I said two things negative. This says if it's unbounded, then it's not compact. The contrapositive would be if it is compact, then it is bounded. All right, any compact set is bounded. All right. I've been saying a lot of things. We gotta go in a moment. Let me just summarize here. Any compact set is bounded. We also said a few moments ago, any compact set is closed. This is actually the way to think about compact sets. Any compact set is, put them together, closed and bounded. All right. That's the standard way. When you mention compact set in R to me, what I think of in my mind is a set which is closed and bounded. So I'm going to write this as a theorem. A set is compact if and only if, this is actually if and only if, it is closed and bounded. All right. So something like a closed interval, or just a finite set of points, or the Cantor set, it's got to be a closed set and also bounded. That's what makes a compact set. All right, I think maybe we'll leave it at that for now. We'll talk a lot more about compact sets next time.